I don't usually have this problem of having a degeneracy between the coefficient and the variable, but you guys did this to me. Here, to make it more exciting, make this like 6x x to the 11th, let's say. There we go. So, oh yeah, that's well, I mean, that's the thing is if I have you guys have your phones on the test, then that's what will start happening. Is that I would no longer care about having nice problems. I would just give you problems. Right? So do you notice there's a point to doing this, you guys, which is it doesn't matter what you put in the numerator. The partial fractions is the same. Partial fractions is just based on what's in the denominator. All right? Let me show you another one. What if we had x plus 4? Oh man, what's going on here? Keyboard problems. X plus, I'll find 2 squared plus, I don't know, 1 oh, come on. I'm hitting the wrong key. Cube that thing. There, that might be it.
You're missing a parenthesis.
I might be. Nope, I'm not. So yeah, this doesn't, I mean, I've got, what's my denominator here? It is a irreducible quadratic cubed. What does Wolfram alpha tell us the partial fractions do? Oh. So yeah, this is part of the problem. So this comes from the long division, all right? And then see what does Wolfram alpha do? Complex, right? So if you're willing to use complex polynomials, you can always decompose any rational function as a sum of reciprocal powers of your factors which appear. Like it, basically, if you're willing to use complex, you can always make it look like this. But we don't want to do that, right? So sometimes Wolfram alpha is like too smart, you know? It's like, that's not what I want. I wonder if I put real there, if it'll fix it. Sorry, I should stop playing with Wolfram alpha in class time. Solve. I didn't say to solve anything. All right, fine, whatever. All right, Wolfram alpha, you're dead to us. Yes, power. Here we go. All right, so let me write it out. If I had 3x squared minus 7 over x squared plus 1 quantity squared, all right, times, let's say, x plus 2. All right, just to make it interesting. So I'll do the easy part first. That 1 over x plus 2, that gives me a over x plus 2 in the decomposition, right? Then I've got an irreducible quadratic squared. So what goes on there is we do plus bx plus c over x squared plus 1 plus ex plus f over x squared plus 1 squared.
Why do you skip d times to c?
I just wasn't feeling it, I guess. I don't know. I mean, you can make these letters whatever you want, right? I mean, you can, the names of your enemies. I mean, it doesn't matter. Just you need variables to figure out. These are placeholders, but okay, fine. It's bothering you guys. So D there, there. As a check, 1, 2, 3, 4, 5 coefficients. What's the degree of my denominator? Squared times squared is fourth. Fourth plus 1, fifth order denominator. So we got the right number of coefficients there. Yep.
So what exactly does like the letters represent? Like does A represent is 3 squared plus 7, or is it?
A is A, B, C. These are constants that we can find to rewrite the fraction. So like, let's undo one. Suppose I've got 3x plus 7 over x squared, you know, plus 1 squared, yeah? Plus, I don't know, 2 over x squared plus 1. So I'm starting on the other side of things. What happens when you add those fractions? Right, I just make a common denominator, multiply it out. So what partial fractions is really just saying is that you can undo this, you know? And that if you put constants like we have, that is sufficiently general to get all the cases. All right? Or we could try another one, like 3x plus 1 over x minus 2 plus 3 over x plus 1 squared. When you combine those, what happens? When you add, you make a common denominator, you get, you know, 3x plus 1 times x plus 1 squared plus 3 times x minus 2 divided by x minus 2 times x plus 1 quantity squared. So if I'm, and of course I could multiply this out, right? But the point is, if you have a denominator like this, it stands to reason that you can rewrite it as a sum of things like that, right? Although, what's the thing? The thing is, I mean, this one just has these two pieces, right? But if I had another piece like over here, say, you know, 6 over x plus 1, what would that change? If I added this piece over here, what would that add? It would just add what? Just plus 1. There's no square on that one. So I don't know in advance of undoing one of these common denominator rings whether or not I have just one of these guys or one of these guys and one of those guys, right? So I have to put both to allow for the possibilities. That's what partial fractions does. Now, I think I have a proof of partial fractions. Since you're asking me for a proof, that's what you're asking. I don't know if you realize that or not, but that's what you're asking for. Let me let the screen warm up again here. Let's do another example while we're waiting for the technology. All right, so now I'm gonna put the ball in your court, you guys. So usually I make these more interesting by combining the partial fractions with factoring. So you guys tell me, partial fractions for, oh man, if I could remember a number. Thank you. 7? All right, so what if I had 3x plus 1 over x to the 4th minus 81? What if I had x squared plus 2 over x to the 4th plus 5x squared plus, oh, I don't know, 6. How would I do those? How would I set up the partial fractions? A factor. How would you factor those?
The first one's perfect square, so it would be squared plus 1 squared minus 1.
Say the first one is a perfect square.
And then you can factor in squared minus
So you got x squared minus 9 times x squared plus 9, right? So, by the way, my notes have like some pretty hard examples. There are examples in my notes on partial fractions where I actually introduce a technique of linear algebra to solve the system of equations. See, because like generally speaking, the equations for the coefficients, they tend to get all intertwangled. It's a technical term. So I actually run through like how to use a matrix technique to solve it. I don't expect, that's not like required for this course, all right? There's things in the notes for partial fractions which are like obviously something too complicated for me to put on a test, right? I just want you to be aware that there are ways to solve the equations, and I show you some of those ideas. But we'll do more explicit examples as we go on here. So you guys told me 3x plus 1, so that's x squared. So this basically factors as x plus 3 times x minus 3 times x squared plus 9, right? That's what you got. Well, that's what you should have got for factoring this, because it's x squared minus 9 times x squared plus 9. X squared plus 9 is irreducible, but the other one factors. And so that means partial fractions here, a over x plus 3 plus b over x minus 3 plus cx plus d over x squared plus 9. And how about the next one? So I think that factors x squared plus 2, x squared plus 3, right? So we've got a pair of irreducible quadratic factors in the denominator, and so we've got ourselves like an ax plus b over x squared plus 2 plus cx plus d over x squared plus 3. So those would be the partial fractions there. Yep.
You just cancel that x squared plus 2.
Oh, I'm sorry. There you go. I made it 22, so otherwise, yes, you really should just cancel them. Thank you. Man, I keep doing this. It's good that you're asking me these questions, but... so this, in my notes, is a proof of the existence of partial fractions. So what I'm doing here is I'm taking an arbitrary rational function, and I think I use the complex argument. So I take the denominator, factor it as a product of possibly repeated linear factors, and then I claim that the following equation has a solution. In particular, f of x equals p of x over q of x is this. So the equation that you're trying to find is this, these coefficients a1 through an. And so what do I do to prove it? I multiply both sides by the denominator. It gives me this. And yep. And then I plug in the first root. And the first root makes everything collapse down except for ak1, which is the top. That's like the top thing in the first root pieces, and that gives me this value. And then I plug in a2 and so forth, and so I pick off the top coefficient of each root by just evaluating. And then what do I do? Then I differentiate the equation and then plug in the roots again, and that picks off the next deleting coefficients. And then you keep doing that, you'll have formulas for all the coefficients. And then you have to deal with the case, well, some of the roots can be complex, and if you take a sum of like complex factors and you put them together, you get one of these irreducible pieces. It's basically the complex conjugate pairs add together to give the irreducible terms. And when you have a squared complex factors, those give you the irreducible squared terms. And so, anyway, I do have a proof of this, but it's really not something I should talk about in lecture. But you're asking the question, so like you made me do. It's all your fault. Obviously this is for math majors. This piece, But the actual proof that you can always do this is involved, right? And this proof is even incomplete, all right? Like, it's a good sketch of a proof, but my brother wrote a paper on partial fractions where he showed that partial fractions extends past real numbers into actually a number of interesting number systems. But anyway, I think I'm out of time. So my brother is a mathematician. Like, he's not like an English professor who wrote that paper, just so you know. I mean, it could happen, I guess.